Hi, my name is Jaidyn Fontenette, and my presentation is going to be over hyperbolic functions. So hyperbolic functions were introduced in the 1760s independently by Vincenzo Riccati and Johann Heinrich Lambert. And that's Johann right there. Hyperbolic functions have similar names to the trig functions, but they are formed by taking combinations of the two exponential functions, e to the x and e to the negative x. These functions simplify many mathematical expressions and occur frequently in mathematical and engineering applications. While ordinary trig functions stem from a circle of unit radius, hyperbolic functions stem from a right half of an equilateral hyperbola. In this presentation, we will be learning about hyperbolic functions, its formulas and graphs, as well as real-world applications of hyperbolic functions. Here are the equations and their definitions of hyperbolic functions. So as you can see, this is what the hyperbolic sine is, the hyperbolic cosine, and the hyperbolic tan. These are just the opposite of hyperbolic secant, hyperbolic cosecant, and hyperbolic cotangent. Here's the graphs of these. And as you can see, I split them up of their opposites, sine, tan, and cosine, and hyperbolic secant, cotangent, and cosecant. So here we are, we're going to consider this problem out the textbook where the limit of hyperbolic tan x is going towards infinity. And obviously on the graph, you can see that it's going towards 1, and the answer will obviously be 1, obviously just by looking at this graph. But if you didn't know that by just looking at the graph, here it is algebraically. So as you can see, this would equal infinity over infinity. And since this is an indeterminate form, we will use Hopital's rule, since it's infinity over infinity. His rule states that if you have an equation that has an indeterminate form, then all you need to do is differentiate the numerator and denominator, and then just take the limit. And there he is right there. So when considering this algebraically also, going from infinity to infinity, you can see that it'll end up equaling hyperbolic sine over cosine, and those are the definitions, which turns out to equal e to the x plus 1 over e to the x, and then so on, which will still end up being infinity over infinity. Moving on, to break it down even more, you can see that it equals e to the 2x plus 1 and over e to the 2x minus 1, which then ends up equaling 2 to e to the 2x over 2e to the 2x, which ends up being 1. Boom. So the real-world application of this. So one physical application of hyperbolic function involves hanging cables. So if a cable is suspended between two supports without any load other than its own weight, the cable forms a curve called a catenary. High voltage power lines, chains hanging between two posts, and strands of a spider's web all form catenaries. And as you can see, that post also forms a catenary. So what we learned today is that the formulas and definitions of hyperbolic functions, we learned what their graphs look like and who discovered these functions. We even learned what Hopital's rule is and how to make your own graphs and labels in GeoGebra. So me and Professor Illich, we learned how to make a label through GeoGebra to just define your line or whatever you made. And so we went to the snippet tool, and then we went to go press text, and then you pick where you want it, and then you can press the latex formula. But if you want to advance it and easily like put x over 2, obviously what I did in my last slide, then all you have to do was press advance, and then it'll show up what shows up in that text box right there. And for A and B, you put what numbers you would like to put in there. And here is my works cited.